Thanks all for coming. Indeed, I'm going to talk about virtual threads and why the completable future no longer has a future within Java. And this is all brought to us under the name Project Loom, which is probably not unfamiliar to you all. So I'm going to talk a little bit about Project Loom and then give some background, how we came here, why we need it, what have we seen in the past few years. Then we're going to dive into a few concepts from Project Loom: virtual threads, structured concurrency, and scoped values. And I hope after today you get a little bit of a feeling of how it works. If you're not already working with it, that you're feeling confident to start working with it. And I hope during this session, whenever you have a question, please don't hesitate to interrupt me. I like to have it interactive, so please do not wait until the end. So Project Loom started in 2017. Then they started to think about, okay, how can we make it such that Java can be more performant and work with all this reactive stuff we see around in the world. It's quite a long time, and now finally since Java 21, which was released in September of 2023, it came as a final feature in Java, which means that you can now finally completely use it, although it was already in preview in 2019, or in Java 19, I mean. And it doesn't stand on its own because virtual threads need some other features, and we'll dive into that later on. And that is scoped values, which is now in its second preview, so probably in the next version it will be made final. And the same goes for structured concurrency, which if you're coming from Kotlin world, it sounds pretty familiar probably. So Java threads, it's quite funny that when Java started, they had virtual threads. They had green threads, they had a lot of user threads which were working on one operating system thread. And at some point it didn't perform well enough because our machines were growing and we got more strong machines, so we wanted to have more concurrency and more abilities. So they had another feature which was the platform threads, where the VM threads are a tiny wrapper around the threads which are in your Linux kernel or in your other kernel. So they abandoned the green threads because they were not as performant as the platform threads, and at the moment it was working way better. So what happens is that a Java thread is just a thin wrapper around a kernel thread, and for every thread you spawn in your program, it also creates a thread on your machine, which is quite expensive, but you get to lean on what the OS gives you. So the OS has really good scheduling, so we can rely on that, but it means that they are expensive. Which means you don't want too many of them. And we have a lot of programming models which just create a thread for every request we get, for instance, like where you get a HTTP request, create a thread and work on that. But with the growth of the internet, it was not feasible anymore, and we wanted to have something which scaled better. So this was the thread per task, right? So it's limited in our resources. At some point your machine will blow up if you're having too much requests, too much threads. But the programming model is really simple, right? You just write your program in one thread of thinking, and it's what we are familiar with. But because it was really expensive, at some point they said, well, let's limit it a little bit and let's create thread pools. And you can submit work on your thread pool. So that means that you can have a lot of tasks which are performed by a small amount of threads, which needs to be synchronized then, and then you have something which comes up, which is like blocking a thread. What happens when you block a thread, and what if you have a pool of a few threads, all threads are blocked, then your program cannot progress anymore. So that gives you new problems. Although it solves some other problems. And if you work with it yourself, then you have to manage this thread pool. But then there came some frameworks which help you do this, right? So We don't want to have a thread pool, submit tasks to it, and manage everything ourselves. So we get into this asynchronous programming model where there are frameworks that help you, but it's a completely different world we're entering. So we had a single thread where we were making steps, and every step does something, and if there's an exception, you get the exception, you get the whole stack, you see what went wrong, what was the path to get there, and what was the path back. But now, suddenly, you get something like what you see in the lower left corner. Like, okay, there's an exception, it's here, and it came from thread run. So you do not see anymore, okay, what was the path to get there, and how can I debug it? So it's really difficult to debug this kind of code. And it's a different mindset when you start writing it, which also makes it different. But it helped us a lot, because when you're writing this in a good fashion, and you do not write any blocking code, and that's a really important one, then it becomes really fast, and you get this stuff like, oh, let's make reactive programs, and we can handle massive amounts of requests, and our machines become way more responsive, and we need less hardware for the same applications. But you have to be mindful about how it works, and that you do not use any blocking code, because that can ruin your performance, because in this programming model, we really would want to go to threads per core, so that you have a thread pinned on a core and it can constantly work because there's nothing blocking. Every time there's something work to do, it can perform the work on your CPU. The moment you start blocking, either by just doing a simple thread sleep, then that thread is pinned to your core, and it can no longer progress. So if you have an 8-core machine and there are 8 tasks which performed a thread sleep for 1 second, your application is completely stuck for 1 second. So we want to have the benefit of these reactive programming models, but we do not want to have the burden of the programming paradigm to do this. And we do not want to rewrite all our current applications in a new programming model to say to our customer, well, now it's a little bit faster. So they thought about virtual threads, green threads, or another name which pops up regularly, which are not tied to one core. So can we make it such that we have the idea of a thread, but it's not tied to an OS thread, but our GVM can schedule the threads on the platform thread, so that you can do whatever you like, normal programming model, and then schedule it on the platform threads. These are still underneath there, but then have fewer of them. So let's look how that looks like, going from platform thread to where we are now. So normally, if you want to create a normal thread, we can just say thread, and we can create a platform thread, and we can let it run something and let it sleep for 1 second. That's just really plain, simple, spawning a thread. And is it readable, by the way? Yeah. So this will just perform this task of printing something to the outside world, and the application will wait until all our threads are completed before the application will exit. So now it's just the programming model is the same, but we can just say, okay, let's make this a virtual thread, and it looks exactly the same, except for one thing: we don't see any output. That is because all virtual threads are daemon threads. So that means that the application will no longer wait for this thread to complete. So it will just spawn the thread and continue on, and then at the end it will not wait for it. So if I just simply do a thread sleep here of 2 seconds, let's make it a little bit longer, then I will see it. Or of course, I could just, which would be the normal way, join the thread, wait for the thread to complete, and then continue onto my main thread and let it handle the thread itself. So the programming model is exactly the same, which is really something, an accomplishment, I think, from the team, that they made it such that you do not have to think differently. It's just normal, regular thread. So now let's do something new, and let's do the same thing, and let's make a few of them. So let's make 8,000 threads. What's wrong? Let's jump to example. Luckily I have a cheat sheet for myself. Here it is. So now we make, well, these are 10,000 threads. And let's first start with creating the platform threads. And we'll see that the application can no longer perform. If we start this, what did I do? I did paste into the wrong thing, always demo. Let's try again. Is it correct now? This should do it. So you saw it started with an exception, because it tries to create all these threads, and at some point, with being above something about 8,000, it shows that my laptop is not able to create so many threads, so many platform threads. So it will crash, and it can either crash because there's no memory, because platform thread needs 1 megabyte of memory, or some other resource handles in your kernel or whatever. So it's not able to create it, and at some point, well, if I create 8,000, I'm able to run them, but we will see that it takes some time to complete, even though I just said, well, wait 2 seconds. Now let's just change this. And let's say, well, now let's create virtual threads. And now I will go back to the 10,000 virtual threads. And virtual threads are really lightweight, so just complete it in a blink of an eye. Well, not in a blink of an eye, because I said wait for 2 seconds, but it's no longer taking so much resource from my hardware that it takes 3 seconds to create all these threads and let them all complete. This now takes what I would expect, a little bit above 2 seconds, because it has a loop of 2,000 which it has to complete.
You did not change the join now, or is it? Oh,
No.
It's still there.
No, the only thing I changed now was just this platform or virtual. Yeah, here below.
Had to join.
Yeah, it joins. By the way, if you haven't seen that yet, these are string templates which are also coming to Java. So they no longer have to concatenate all the strings, but you can just have templating in it, which we know and love from all the other languages like Scala and Kotlin.
In 21 already, or in?
It's already available in 21. In 22, it's in, I think it's in second preview. And they made a small change to it, but different talk maybe. But yeah, it's coming, which is nice. And there are a lot of nice things coming to the Java world recently. Okay. So normally we just don't create the threads ourselves, right? So let's go a little bit like what I showed on the presentation. Normally you use an executor service. So here we have the executor service, and there you can say, just like with the other executor services, normally we would say thread, not virtual thread, new thread per task executor with the default executors, so, like this. And this will just create, every time I submit a task to the executor service, create a thread for me. So if I would reinstate this big loop, here, this loop. Copilot is really nice to help you out. So this will have the same problem, right? So it will create a thread for every task I submit to my thread pool. And it will blow up. So therefore we said, okay, now let's use a fixed thread pool, for instance, and then let's still use a massive amount of threads, because 1,000 threads for an application is still a lot. And now it will work way better, but it takes much longer. Because now it will submit 1,000 tasks. Those 1,000 tasks are all blocking. They're all waiting to complete before the next 1,000 tasks are submitted. So this will take 20 seconds. And the good thing is now that we can think differently. And so, well, actually what I want those 10,000 tasks to just execute, to just run. And now with this virtual threads, we just have that under the button to just use another executor. And now it's done in 2 seconds. So again, this is something which they baked into the platform. We saw creating a thread is the same API, but now also the executor works also the same way, whatever you choose. And now you can just use, okay, let's use the virtual threads underneath. It's also something which is now baked into multiple platforms where you can just change the configuration and say, well, use virtual threads. And then it will use a scheduler like this to submit every task, and then it will create virtual threads instead of the old platform threads. So just for a little reference, I showed you the different program paradigm. So if you're familiar with Flux, with Project Reactor, then if I want to do the same thing, I would write something like this, right? So I have a range to 10,000, and I want to do for every step, I want to do, can I zoom? For every step, I want to wait a second, and let's just use a bit of a naive approach and just sleep. Oh. This would be a normal implementation when someone starts Project Reactor and think, okay, I want to do something, and I want to wait a second, and then I want to continue, and I want to print something out. So, yeah, I would expect to run this quite fast. Flatmap has a default concurrency of, I think, 64 or 256, I'm not sure. But if I run this, I get something completely different. There's just one thread running. Because there's nothing in this code which releases it and tells Project Reactor that it can reschedule it. So it's just doing it one by one until it runs into something where it can say, oh, now I have to wait, but now it's better to split it out. So this is something which you have to be really familiar with, and this is what I meant with being familiar with this different programming paradigm, because if we do it in the normal way, in the way that it should be, like non-blocking, then you would say delay the elements. And if I now run the application, then it will do much more concurrently, right? So now you see that it's much faster, and if I really speed it up, then because you can say how much you want this application to do concurrently. So if I want to say, well, let's do 10,000 things concurrently, then wow, it's as fast as the virtual threads, which is nice. And I don't want to hit on this programming model, but it's different. Just you have to be mindful about what you're doing. And whenever you use a library, you have to question yourself, is this blocking? And this is a difficult thing. So let's continue. Are there any questions? Remarks? No. Okay. So the thing with the virtual threads is that they live on the stack, which means that they can also, or their stack lives on the heap, so they can be garbage collected. So it's just like everything you do in your application can be garbage collected, and the virtual threads with their call stack, they can be garbage collected as well when they're done. And as we've seen, there are always daemon threads. There's no way to change that, so it's not possible. We will look later on into a little bit deeper into the structured concurrency, because there we can see how we can work with that. They have a fixed priority. I personally didn't work with priorities in threads. I don't know if anybody has ever changed the priority of a thread. Probably for some frameworks it makes sense to change it at some point, but it's there. And yeah, it's really cheap to create a virtual thread, so you don't have to hesitate, well, should I create it or not? You just can create it, can create a lot of them. And we can see here, this was an application with a simple application, 5,000 platform threads. If we use virtual threads, yeah, this uses 78 gigabytes of memory total. And for the platform threads, well, I would expect something around 5,000, and it was something around 5,000, because thread has 1 megabyte memory. Let's see. So yeah, so the thing is different because the memory of platform threads are outside of your heap. If you look at the heap usage, then with virtual threads, of course, your heap usage of your application is bigger. So the virtual threads can make your current applications much more scalable with minimal change. All you have to do is every place where you create a thread, change that into virtual thread, and it should just magically work. One thing to note though is that you should use virtual threads for scale, meaning for if you want to run things in parallel, want to do a lot. They're not faster threads. So if you have a compute-intensive task, it doesn't make real sense to create a virtual thread for that, because it just has to run on a platform thread, and once it's done, then it can release its work. And that's the same thing for virtual thread or a platform thread, no difference there. So when there's a lot of concurrency, and most of our business applications, I think, can benefit from that, because a lot of our applications are just waiting for responses from file systems, databases, whatever. Nearly everything in the JDK now works with virtual threads. So all our concurrency features which are in Java Util Concurrent work with it, meaning that if you run into something like a semaphore where you have to wait to something to become available, the virtual thread will just release the platform thread underneath, and the application will continue. All I/O works, so you don't have to think about, okay, I'm now running into this, will that block the platform thread? No, it will just work. So now let's look at the future.
One question?
Yes.
So you're saying indeed that the virtual threads are not just faster threads, but is there any reason to use platform threads now? Because yeah, it's maybe a little overhead, but if not that much, then you can basically just say, well, just use virtual threads all the time.
I would do that, yeah. So maybe if I have more experience with more applications, I can give a better answer of specific examples where you have to do it. But well, if you have a compute-intensive application and you know that, then it doesn't really make sense to use virtual thread everywhere. If you can choose and you're making your own threads for yeah, then you can think, okay, this is compute-intensive. Let's make it just a normal platform thread. But you could still use it, and I don't see a real downside to it that it would hinder your application. But it's just to be conscious that it will not make your application faster to use the virtual thread. So now let's look at another example. And that goes a little bit more, because now we just spawned futures or threads, which just write something to the console. And what I want to do now is have a more application, more something that does a little bit more, like what our applications does. It goes to one database, it goes to a service. We need to combine the results from that. How would that look like? Copilot already spoils it. You would generally have a thread executor and then submit something, and what you will get back is a future, right? It will give you a future, and something which we are taught to never do is to call get on a future. But now with virtual threads, that's all changed, because it's no problem to block, because it's not really blocking anymore. It's just waiting for the result. So it now becomes quite simple. I have two tasks, one to get the time, one to get the date. I will submit that. And then in the end, I will just want to print it with both the results. And if I just run this, it will just wait in total 3 seconds, because getting the date is really expensive. It takes 3 seconds. And then it will print the result. But now the thing comes. Let's say that the get time blows up. What would you expect to happen? Exception. Immediately?
Yes.
Okay. No. It takes time because the executor service spawns these threads. They wait for all these threads to complete. And one thread does not kill the other. As far as the JDK knows, you want this task, you spawned it, so I will wait for it to complete. I'm not at liberty to say that I want to cancel it or whatever. So this is something where you start thinking, okay, how does this work? Because there are applications in Kotlin, you have the structured concurrency, and other languages you have other paradigms or other stuff to make this work. And this is where we need more functionality from Project Loom. So not only the virtual threads, because this is working with virtual threads, it's working perfectly, but I want to have something like a kill switch whenever something breaks, that it stops working.
Is this different from when you're using platform threads?
No, same. Let's try it out. Don't believe me, my word. New thread per task executor, executors. Luckily, I'm not lying. But this is the beauty of it, right? So this thing, like, okay, it works. Does it work the same? Yes, it works the same. It seems like the same. It feels the same. The only thing that changed is the execution underneath. That is not hugging up your resources to wait for the result. It just works. And it works the same way as we've already familiar with. And then on top of that, we get this performance. So one thing, do not pool virtual threads. They're not meant to be pooled and to be reused. That's something we did because, yeah, threads are expensive. Let's pool them. If you want to do something about concurrency, because that's also something where you can use it for, like create a thread pool of 5 threads, and then you're certain that there are only 5 executions at the same time. But we have other mechanisms for that, semaphores to do that, and to make sure that there are only 5 tasks running concurrently, and whenever it is done there. So it becomes more clear what your intent is, and it's not hidden somewhere in, oh, it's a thread pool of 5, and therefore it's 5 concurrent. I lied a little bit in the sense that virtual threads work with everything and you don't have to think about it, because whenever you run into a synchronized block, then it will block. Because it doesn't really know when it can release that, how should it work with that. So that's something that it cannot free the platform thread underneath. and also when you're executing native code. So if you're doing something to call some outside, then you also have to know that that will block the thread on the platform thread. But apart from that, nothing. Also, be careful with thread local. If you put a lot of resources in that, it can give a lot of overhead in copying. And they have something better, which works better and works more clear, which we're going to look into scope values. And we have some tools from the JDK which will help us out. The flight recorder, where we can see events that we pinned a thread, or that we use thread local. And you can also add a property to dump it as a stack trace in your logs. So that was about virtual threads. And now we're going to look a little bit about virtual threads, the goals which they set about, and let's check them off. They want to scale traditional applications with near optimal hardware utilizations. Well, it's completely the same as what we did with the reactive frameworks, where we have to build it differently but make it scalable. Now they made it with virtual threads. Minimal change. Well, we've seen that that's true, right? The API looks the same. And which I didn't really show, but you can guess a little bit. So like the debugging and profiling of virtual threads is the same as the normal threads. So you get the good stack traces instead of these nasty stuff where you do not know where it's coming from. So it's really, these were the goals which they set out for virtual threads, and I think they achieved amazing results with that. So now with structured concurrency, because what we've seen now is that, okay, I created something, I called two services, get time and get date, but my application does not stop when something breaks, and that's something what I would want to do. And also I want to raise threads, like calling two services, get the postcode from one source and from another source, and the fastest one gives me the result, and the other one I'm not interested anymore. And that's something which structured concurrency will bring us, and people coming from Kotlin will be familiar with that. And it's now in second preview, and they made a really small API change, which I'm not going to bother you with. So let's continue with this example. And what I now have to do is I have to change and no longer use the executor service, but I have to use something which is the structured task scope. So I can structured task scope. And here you have to choose whether you want to shut down on failure or shut down on success. So if one of my threads fail, stop all the threads. Or if one of my threads succeeds, then stop all the other threads. So in this case, I want to shut down on failure, because if the time call fails, then please stop, I'm done. It's no longer submit, it's in the executor it's the submit, but on the task scope they call it something else, they call it fork. So here you fork your task, and what you will get back is a subtask. And if we run this now, it will not work. It will give us an error. Owner did not join after forking tasks. So what we did here, we forked two tasks, but we did not say at what point we expect a result here back. So what you need to do here is we can, on the executor, we have to call the join. And now you can do, you can say this is convenience. Okay, now throw if failed. So if one of these failed, just throw that exception. I do not want to bother with it myself. I do not want to do further checks. If you're done here, throw immediately. So it will run up to this. Whenever it sees the exception, it will just throw it. And again an exception, but this one we expected, because I can shoot here. In the get time was this throw exception, and this is the same thing we see here now. Right, so immediately now it runs into an exception. Okay, just stop everything which is in my scope, and then bubble up.
You can also try catch that join, just throwing, and the throw if fail is just an helper to.
Here, try catch around this.
Yeah.
But what would you want to do?
I don't know, but you said that throw if fail is a.
Yeah, you can. So if you do not want to do this, then you can on the executor. You can get the, what was it? From both you can get the status, I think. Date and then state. So from different tasks you can ask the state, you can get the result, and you can work with that. I think regularly what you will do is just makes more sense to just pop out here and then work with that outside and then handle that. So keep it clean here and then handle it upstream. So these are the scoped values. And of course, if you want to have the succeed on success, then that works the same. So the last thing which they added under Project Loom are the scoped values. Currently we have the thread local, but there are some problems with thread local. They have unconstrained mutability, so you can change it from a lot of places. They have an unbounded lifetime, which means that they leak into other processes, so you really have to make sure whenever you stop using a thread that you unbound it, you remove the context from it. Yeah, it's really expensive, so that means that if you have a thread and it has thread local context on it, and you create another thread during the run of the thread, the context will be copied into the other thread, so that can become quite expensive. So in this JEP, the scoped values, they thought of a better way to do it, and they call it scoped values. And the most important things of it are that it has a constrained lifetime, meaning that you can say, okay, here, this is the point where my scope starts, and whenever the scope ends, then it will remove the context. So the context will not leak, it will be garbage collected or what, it will be gone. And it's also immutable. So it's not possible during the span to change the value which is in there. So you can normally use it for just putting something on the thread, and then it will like, oh, this is for this user, and then everywhere it can, somebody can get it out of it. So I can look in a little bit into how that goes, less interactive because this is quite convoluted. Let's zoom a little bit. So a little bit of context. What I did is, how it works is you create something like, this is the same with thread local. You create a scoped value, you make it normally a private static. And you say scope value and make it a new instance. And then you can, in this case it's a string, put something on it. And this is just a placeholder, right? So I define something and now I can use it. Now if I want to use it, I have to say I want a scoped value, and this is where I start. And this is a combined, so you have a run and you have a where. You can, with where you define it and run, you can run something in it. This is combining, using this context, set it to a value and run something. So this is the most convenient method to use. So I want to have this context value. I want to give it the value test value, and then I want you to run this block of code. So in that scope, everything in that scope, and whenever it goes deeper and deeper, it will just propagate this value of context. I have a value, a function or a method show context. What I do is I do a context is bound, where you can check if the current thread has this context attached to it. You can also just get it and then it will throw an exception. This is a little bit more nice. So if it's bound, then I will just print it, that is bound with the value, and otherwise I will print that it's not bound. So that makes sense later on when I show you what comes out of this. So create a context, then show me the context, then start a virtual thread and show the context. Then create a new scope, structured concurrency, right? So create a new scope. I want to fork and then show the context. And then at the end, I also run something which is a nesting function where I create another few nestings. So the output of this is more interesting in the end. And it will show in the parent, whenever I start, this is the first line, show the context, and then it's the parent. It's the test value, right? That's what I set it to. Then we have this unbound virtual thread. We just spawn a virtual thread here. We do not know the lifetime of it because it's not structured, right? It's just throw it, let it run. So from the perspective of the scoped value, it cannot guarantee that when the scope should end. This is why it's not bound. The value is not propagated with just creating a virtual thread out of the blue if you do not do it via the structured concurrency. Then I do this via this structured concurrency and I fork this. Then we have a scoped virtual thread, right? So here we can be certain that at some point we will end it. So here we see scoped and yeah, lo and behold, we have the same test value. And then we go into this nesting value where we can just give other values to it. And the most important here is that at the end, so if we nest, we can give other values to it. But whenever it goes out of its scope, it gets the previous value back. So it's really layered in that sense, which can make it powerful, right? Because you just know, okay, in this scope, this is the value. In this scope and below is this value. But if you pop out, yeah, what was the scope? Yeah, you go back to the scope it was previously, which is really handy and really powerful. And then in the end, if we're outside this run, right? If we then try to look it up, then it no longer has a value. So it's cleaned up, it's gone, and then there's no leakage.
Can I ask a question?
Yeah, sure.
The point where you created a single virtual thread with the unbound VG virtual thread, would it show something different if you joined that thread over here?
I can join it.
I assume not, since it's not bound, but
Well, let's surround it with try-catch.
Still yellow.
It's still not bound because the join happens after. And from a programming model perspective, whenever you start this thread, you have to pass it the context.
yeah.
And because it's created in this way, we cannot know what happens after. So we do not know if at the end this thread is also gone. And therefore, yeah, we cannot propagate it because then we would leak the context.
Yes, that makes sense. So what I would expect though in the logs is that because you join, you basically wait for it to complete before continuing.
Yeah.
That doesn't seem to happen as well based on the logs.
Here I wait for the thread to continue, but it cannot in hindsight add the context to the thread that is already running.
I understand, but if you look at the order of the logs that pop up, I would expect that after parent, I would see unbound VT.
Here.
Yeah.
Oh, that's interesting. Yeah.
Might be just a race condition with printing, but
Yes, I think so. Let's just. Let's see what. Yeah.
okay.
Yeah, that's something, well, that's life with concurrency, right? If things run in parallel, then it's like, okay, why is this not in the right order? Yeah, because it's just racing each other and you don't really know how it works. And certainly with going to the console, then, like, and sometimes it changes if you log to the console, right? Your application, yeah. Nice hiding bugs. So, in conclusion, if we look at virtual threads, what they've done since 2017, they thought of a model to not change Java, but make it way faster in highly concurrent situations. Do not change the programming model so that every developer which knows and loves the current programming paradigm can just work with that and use that without having to learn a new framework, a new paradigm. And as we've seen, they did an amazing job to accomplish that. I think it's worth waiting for the scoped values, or more so the structured concurrency. That will become final, I think, in the next release. And then, yeah, it's really powerful to create your applications using this. Certainly at this moment, if you're using Spring, it's just a matter of changing a toggle and you're using virtual threads underneath. And you do no longer have to think about, okay, how can I work with this? So I'm really interested how this goes, what will happen with, for instance, coroutines in Kotlin. How will they go forward? Will we see the virtual threads shine through there, or does it change how that works there? Do they keep it the same? Do I still have to write suspend everywhere? But yeah, certainly for stuff like Reactor, yeah, what's the use case? It's such a complex framework, and if we can just use the normal frameworks we all are familiar with and which are easy to learn, much easier than all this callback frameworks. So I'm really looking forward to what's going to happen in the next months/years. So with that, thank you for attending.